if we write the Duffing system again, we'll write it this way: x dot equals y, so in first order form, y dot equals x minus x cubed minus delta y. Instead of f, I'm going to call this epsilon cosine theta. That's sort of a hint. I'm going to look at small epsilon. And hold on, not theta. I'll call the forcing phase phi. So we are letting phi equals omega t. And then what is phi dot? Phi dot is pretty easy. It's just omega. So now we've got a 3D nonlinear set of differential equations. Looks like damped forced motion in a potential energy well that looks like 1/2 x squared plus 1/4 x to the fourth. If we didn't have the forcing or the damping, this is a conservative system or Hamiltonian system, sort of harkening back to when we talked about two-dimensional systems with special structure. So we have a Hamiltonian system where h equals 1/2 y squared and then plus v. But of course, the damping takes away some of the properties of the Hamiltonian system. Remember, Hamiltonian systems conserved area. So we don't have that if we have damping. Damping actually makes volumes shrink. And the forcing does other weird things. Got to take that into account. Now, if we look at what's going on here, we would probably first want to start with the epsilon equals 0 case, maybe even epsilon and delta. So let's just turn off damping and forcing. So that means delta and epsilon are both 0. And that means we don't even have to worry about the phi. It doesn't show up. Then if we were to plot what the phase portrait looks like, it's just going to look like level curves of h. So phase portrait looks like level curves of h. And I won't plot both sides. I'm just going to plot one side because there's symmetry to this system. So don't need to do both. It's x, y. The origin is a saddle point. And then there is some kind of center point that things are orbiting around. This being a saddle point, there's going to be an unstable, actually 2 branches of unstable and 2 branches of stable. And these have to be, they're at the same energy, so they will actually have to meet back up. So we have a homoclinic trajectory on the right side. There'd be another homoclinic trajectory on the other side. I'm going to refer to this point because this point is actually the most interesting. It's P0 or P0 is a saddle point. In this case, it's the origin for these values, epsilon and delta 0. So when I change it, when I change epsilon, I'll be keeping track of P epsilon. And I don't know if that's going to be a saddle fixed point anymore. So this is a saddle, right, fixed point in terms of the classification scheme for 2D ODEs. Other trajectories look like, they just look like, moving around, you get this by some contours H. So these ones inside the purple curve are just going to oscillate in one well. So think of going back and forth. These trajectories that are outside, they will be oscillating around both wells. So it has, think of it as just having enough energy to go between 2 wells. This object, we're going to give it a name, right? There's this part that's leaving, and that part that's leaving, we would call that, this goes beyond just the linear approximation. So we're going to call it the unstable manifold, or W superscript U of P0. And then this part that's going toward the point, this is the stable manifold. And things that start on there will just continuously head towards the fixed point, right? This is, we can interpret this in terms of an ODE. So that's nice. Means if you have a point here, you know, 1 second later it's here, and then here, and then here, and then it'll be continuous. And then as you approach, you'll be getting, the points will get closer and closer because it's just asymptotically approaching in forward time. And then in backward time, it's also asymptotically approaching that saddle point. So something like that, we would say it has an infinite period, and it's going around from one side to the other. Now notice these are the same curve because they connect up. So W U P0 equals WS. The stable and unstable manifolds coincide, but they might not always coincide. As we adjust parameters, things might break. We're going to call this object, I'm going to call it capital gamma P naught. And it is, right now it's just one curve, but I'm going to define the intersection of the stable and the unstable manifold because it might not always be the same. This thing is called the homoclinic manifold. Any initial condition on it, we'll just sort of follow it to its end, forward and backward. They go back to the saddle point. So that's why it's homoclinic, starts and ends asymptotically approaching a certain object, in this case, that saddle fixed point. It's also a separatrix because it separates two different types of behavior. It's a separatrix, it's a kind of a frontier that separates qualitatively different behaviors that we've already described. The orbit about the right well, periodic orbit versus orbit about both wells. This was for the case that epsilon and delta are both 0. So no damping and no forcing. If we now relax that and add forcing and damping, we'll first allow forcing. So let's first add forcing. Before we do that, we want to get a picture of what does this look like in the extended phase space. An extended phase space just means X, Y, and we're using phi. Now, why am I using phi? You might notice something here. X is real, Y is real. Phi, because it represents a phase, it repeats itself. So it's equivalent to being on the circle. That's why I said in the case of forcing, time, the way it enters the equations is a cyclic variable. So it's like the circle. So how do we interpret that? We can plot something. I'm going to take that picture up here and just see what it looks like if I stretch it out in that third dimension of the phase. And you notice we've identified the bottom and the top. What's going on here? If I were to scoot up here and sort of pick an initial condition like this one, this green one, that's kind of like picking this point down here. And then if we were to follow it through time, it ends up here after one phase. And you might think, well, why do we have a phase? Well, we still have omega. So it's kind of like we're strobing something that has no forcing yet. We could still strobe it at some frequency, and that frequency is omega. And then up here, that goes down to the bottom, right? Because the top and the bottom are like a circular variable, right? Again, like, what's the video game I talk about? One of those dumb old ones, Pac-Man. You go in through one side and come through the other. So you could say it's periodic boundary conditions, but it's fancy to be topological and say it's the circle. So this is the circle. So you start down there and then you go up to the top and then you end up here. And then you're down here and then you go up to the top and now you're kind of going around this fold. We're only looking at the separatrix or the homoclinic manifold. So this is the homoclinic manifold in the extended phase space. Hopefully it's clear what's going on, right? And then we'll be here and then you just sort of follow it. So things are just marching along. This point, saddle point, it is this really trivial periodic orbit because it's a fixed point of the ODE. And so you just don't move, but we're giving that a name. So this is a periodic orbit. I mean, in the middle here, there's also a periodic orbit, the stable periodic orbit. But in some sense, it's not as interesting. It's not going to contribute to the chaos. This unstable periodic orbit will. So we could also think of this in terms of a Poincaré map. If we've got a Poincaré or stroboscopic map, then this would be taking points. If I just were to sketch, we've got P0 and then points along that manifold. They would go from here. And then because this is a map, the map is just looking at what happens every period or every phi equals 2 pi. So this initial point goes to here. And we know that it had some continuous path, but if we forget about that, then it's just, okay, this kind of jumps to there. And then this kind of jumps to here. And then this kind of jumps to the other side. We're setting things up because it'll be easier to understand in terms of a 2D map than this continuous picture. The continuous picture is going to get kind of crazy. So this phi axis is the same as time. We identify the top and the bottom. So the Poincaré or stroboscopic map, if we were to think of it in terms of we take everything happening down here, we would call this a Poincaré surface of section at a phase of 0. And then up here is a Poincaré surface of section. That's why the sigma surface of section at phi equals 2 pi. But of course, those are the same because we're on the circle. 2 pi and 0 are the same. So we could say this is we're looking at a Poincaré map. It's a 2D map that takes points, and we're thinking not just along the separatrix, but everywhere. It takes points and then just maps where they go after one period of the forcing, whose magnitude we haven't yet turned on, but it's there. If we called this point Q, then we could call this P of Q. And then this would be 2 iterates of P, Q, and 3 iterates P on Q. It's an invertible map too. So we could speak of where that point Q came from and call it P inverse, and then look at P double inverse, and so on. This thing we are calling, we said this is the homoclinic manifold. So now it's the homoclinic manifold, not of the point, but we're saying of the periodic orbit, this really trivial periodic orbit of just sort of staying at the saddle point and going for some period of time. It's definitely an unstable periodic orbit, because if you're perturbed a little bit, you're going to go along one of those unstable directions, either in the direction we've shown here or the left side. Okay, so this is the homoclinic manifold when we haven't yet turned on the forcing. So this is for epsilon equals 0 still. Now turn on the forcing and the picture will change. So it looks kind of weird now. We've got now epsilon is non-zero. That's what makes the right side different. Forcing has led to what we would call splitting of the separatrix. Over here, the separatrix is just one sheet that keeps repeating, but now it's broken. So the two sides of it, the stable and the unstable manifold, they don't coincide, they intersect. There's more than that going on. Because of this, because we've turned on forcing, there's a periodic orbit, but it's not just at some fixed location in X and Y. So we would call this, think of for small epsilon, we've got a replacement to that periodic orbit that's just vertical. And now we have something that has some wiggles. So if you were to look at it in XY space, there's this sort of unstable loop. But we're not. We're looking at it in this extended phase space. Again, the top and the bottom are identified because it's one phase. But what happens to these points? If I start with that point, and I'm picking a point, this is a point of intersection of the stable and unstable manifolds. And that's important. So we would say unstable, now not of a fixed point, but of this periodic orbit. It's in the intersection of both. Being in the unstable manifold means that as you go backward in time, this would eventually go back to that periodic orbit. Going forward in time, so being in the stable manifold means that, and this is an initial condition which, when followed forward, will forward asymptote to that periodic orbit. And this is a schematic just to give you an idea of what's going on. So then it goes up here, which means it jumps to down here, goes up there, it jumps to somewhere, goes around. These don't coincide. We say the separatrix has split. So if you get into this world of nonlinear dynamics and chaos, you might hear of separatrix splitting. It is one of the generators of chaos, particularly in mechanical systems. And you might be thinking, well, hold on, you said stretching and folding was. Well, this will eventually imply stretching and folding, as we'll get to. Let's call this Q, point of intersection. So we could still define a homoclinic manifold. It's just not this continuous sheet. It looks like it's some trajectories. Q is on this point of intersection. That means Pn of Q goes to that periodic orbit as n goes to both plus and minus infinity. So Q is a homoclinic point. and they're going to play a special role. If you want to see what's going on, there's a lot here. There's another figure I can show that's pretty good. Yeah. So you could see this numerically. So this is something that one can numerically compute. This is the Poincaré map. What I'm showing in the sort of scattershot points are I took an initial condition and then followed it many times. And it seems to fill out this entire chaotic region. And the things that look like closed curves correspond to quasi-periodic motion. Meaning if you start on one of these, then when you emerge, you'll be at some other point on that same curve after one period, and then it'll seem to fill out a circle. So these are all quasi-periodic. All of the closed curves are quasi-periodic. But you notice there's this bounded region of chaos. And the fixed point, the unstable fixed point that's along this unstable periodic orbit is right in the middle of the chaotic sea. It's kind of where X marks a spot there. It's where the red and the blue curves intersect. The red and the blue curves, red corresponds to the unstable manifold, and blue corresponds to the stable manifold. So this is a numerical version of kind of look at just the right side of what we've been kind of sketching, but only on the Poincaré section. And you can't see all the little intersections and stuff because sometimes they're hard to see, but they're there. And there are techniques for finding unstable periodic orbits. So there's ways to do that. So what I wanted to show is this next figure. This is showing, it calls this theta, but you could think of this as phi. So let's start at phi equals 0. This is following one of those curves that's on the, this is the stable manifold. So if I were to draw this, it's the stable manifold of that unstable periodic orbit. And it kind of goes around here, goes around there. The unstable manifold goes around there, goes around there. And you see that they intersect in certain points, but these points correspond to now trajectories if you look in the full phase space. And what we're following is this sheet that's along the stable manifold. So there's that orange trajectory. Now what about the green trajectory? Green trajectory is kind of on the other side, goes to here, and then that goes to like here, and then that goes to here. And if you follow what's going on, if we had done the same thing for that, this part right here, that would also be a sheet in the extended phase space. And that would have gone to map to up here. So it's as if we have this little, if you look on just the XY Poincaré section, it's like we have a lobe. If I were to fill it in, we've got some lobe. But it's this sort of solid piece of phase space that's going up and then mapping to up here. But of course, this is at phase 2 pi. So it's the same as down here, this phase. So that yellow region mapped to this yellow region. And these are called lobes. So lobes are regions bounded by pieces of the stable and unstable manifold of the unstable periodic orbit, which I guess we kind of lost track of it, but it's who knows what it's doing. That's the unstable periodic orbit. If we were to sketch what's happening just on the Poincaré section and only on the right side. So the previous picture was like this, the stroboscopic map. And then everything inside is doing relatively boring stuff. So this is before the separatrix has split. Once the separatrix is split, more interesting things can happen. And in this case, with no damping, the separatrix splits immediately when you turn on the forcing. Like these two, the stable and unstable manifold do not coincide. When you add some damping, then other things can happen. But once the separatrix has split, what do we have? We'll call this point P epsilon is just on the periodic orbit. So here's P epsilon. And then we've got the unstable and stable manifolds that are doing things. Here's the stable manifold. and these might lose symmetry too, but they'll intersect somewhere. So here's a point of intersection. And remember, this is a map. So this point of intersection, if you were to follow it forward, it's going to go, let's call this point Q. So Q is on this intersection of the stable and unstable manifold. Running out of room. We can make more, yay, of P epsilon. So viewed as a map, P epsilon is a fixed point of the map. It's an unstable, in fact, saddle type, fixed point of the Poincaré map. So Q would map to somewhere else. This is P of Q. And what's going on? It's always good to kind of draw the arrows, even though we don't have continuous motion. This sort of tells us this is unstable. It'll be kind of less obvious at some point. And you might say, why did I skip this other point? That's just what happens for there to be orientation preservation. So you have to skip Q skips over an odd number of points to get to P of Q. In this case, it has to be, in this case, I've just drawn one. So this might be called, Q prime, and it would map to P of Q prime, which means these are two different homoclinic trajectories. So if that's Q, this is P of Q, we could also think of PQ inverse. This is P inverse of Q, right, under the Poincaré map. And this bounds lobes. So we could even speak of how these lobes move around. Remember the lobe over here from this drawing on the lower left. Here's a lobe. It's a piece of this Poincaré section. Maybe we'll call it L. L is this lobe. And where does that map to? So if you were to take that entire chunk of phase space, this is what it maps to. And now there's some consequences that show up. And I could try to do it in this sketch and then maybe do a better one. But, right, this is P of Q prime. This is P of Q. There's going to be another iterative Q here, another iterative Q here, another iterative Q. This is on the stable manifold. So that means it just has to asymptotically approach. And maybe you could figure out what the implications are for what these lobes are going to do. I'm going to draw Q prime and its iterates in orange, just so I can keep track. And that's another thing that's also asymptotically approaching. So this purple curve that was, remember, this is the unstable manifold, P epsilon. And this blue curve is the stable manifold, P epsilon. Because this is a Hamiltonian system, the areas have to stay the same inside each lobe. So the area of L is equal to the area PL. That won't be the case once we turn on damping, but it is for now. And so this is going to go like this. And I'm not probably drawing this right, but because these have to keep getting skinnier and skinnier so that they have the same area inside. So this area is this area, is this area, is this area. You can see what's going to happen. These things, well, they're getting skinny in one direction, elongated in the other. We have stretching, right? Because this thing is looping around, following things around, that's what's giving rise to folding. And we could try to look at that more carefully. This situation, this separatrix splitting is also called, I think Poincaré called it this, a homoclinic tangle. So he was the first one to imagine this, as far as I know, and saw this as a cause of chaos in the types of systems he was considering, which were like celestial mechanic systems. I don't know if it was widely appreciated that stretching and folding was also what's going on, because the stretching and folding is more general. But the homoclinic tangle leads to stretching and folding. If you Google stretching and folding, I don't know if anybody has, but you get a bunch of stuff about baking. It's like how to knead dough. You stretch and fold and stretch and fold. Interesting. So this is an animation showing, it's like a perturbation of the, I think the pendulum. So the inverted position of the pendulum, we're showing from like not negative pi to pi, but negative 2 pi to pi to positive 2 pi. And that's why that saddle point shows up twice, and we're showing it's stable and unstable manifolds. The movie is sort of showing us through extended phase space, so through time, through one cycle. And if we start filling in patches, you could see what goes on. These are filling in lobes and just sort of following what they do. And you might notice rectangles that are oriented one particular way get reoriented a different way. And it's all very reminiscent of all the stretching and folding that we've talked about. Here's a computation in the three-body problem. Take a Poincaré section, and it's very similar to what you would get for a time periodic forced system like the Duffing Oscillator. But this is showing a very skinny lobe as we look at different iterates of it. And this is going between two regions. So we've sort of labeled one side of this separatrix. We've called it R1 and colored it blue, and the other side yellow. If we show all the iterates together, this is just showing, everything inside that first skinny red lobe up top ends up in this other lobe, and then they're stretching and folding. If you're in a compact space, right, this is part of what made the strange attractors interesting, is things have to go somewhere. Here, we don't have dissipation. This is actually an area preserving map, but things as they stretch and fold have to go somewhere. This is a nice picture. I think it was hand drawn by, when I was a grad student, one of my, what do you call them, co-grad students? We had the same advisor. He made this, Philippe Dutoit. He did this cool hand drawing. Things are, it's the same kind of situation where things are kind of going around this way. We've got a fixed point of a map with an unstable and stable manifold. But what he's done is just colored two lobes. We sort of focused on maybe this situation up above, although he's making things kind of skinnier. But if you take those and back them up, so think of this as, these are the initial lobes. This is following the stable and unstable manifolds both ways. You get these lobes. Here's at 1, this is at 2. Right, you can see the lobes mapping one to the other. This is at 3, 4, 5, right? We've sort of gone around, and now we're back here. Now this is n equals 6. So what happened? This blue lobe that was outside is now completely inside. The red lobe that was completely inside is now outside. And this is sometimes called, it's like a turnstile, right? A turnstile, when you go inside a building, there's people coming in and people going out. This is sometimes called the turnstile lobe mechanism. And what has happened here, if we were to carefully look at the orientation, this being, this upper curve, color this maybe orange or something. So that, if you were to follow what happened, this is the orange curve over here. So the orange boundary, and the blue one got stretched. So this is doing that step of stretching and flattening. So stretching in some directions and flattening in others. And the complete reorientation is related to the folding. Now, how do we get things intersecting? Here, they're not intersecting, but we can get that. If we were to focus on, let's say, this little patch, I'm going to focus on like what's going on in this little region, and then color things in some certain way. So I'm really close to that fixed point, that saddle point of the map. Here's the picture, and I'm going to take this and reorient it because it'll just make it easier to deal with. Okay, so we've reoriented, and you can see this was like done with colored pencils, some dedication. And we're just focusing on what's happening like in a little square right there. Focus on this little square. And now we've colored the lobe so that at least a portion of this lobe is blue, but we've got a rectangle. I don't know if you could see that. we've got this entire rectangle. The part that's in a lobe is colored blue, and then the parts on the other sides, on either side, are colored red and green. And so this would be at the initial, and then we follow this around, n equals 1. This whole thing maps to here, n equals 2. This maps to here, n equals 3. It seems to have lost the area preservation, but it's hand drawn. And then that goes, we jump over to here. This is n equals 4 and n equals 5 and then n equals 6. So what happened? If we stare at this, the blue part got kicked out. The red and the green stayed, but have reoriented. So if we were to focus on what's happening in just that square, focus on this little square, what happened? Well, this is what happened. So I am showing the square kind of like this. We have that there was a green and red horizontal rectangle, and that mapped to the green and red vertical rectangles. And the blue just got removed. Go away, blue. Blue gets tossed out. And maybe you could see what's going on. You know, what are we going to be looking at? We could repeat this and see what remains in that little square. So this would be, if we were to construct a map, let the map be, took 6 iterates to go all the way around. So if we say the map is the Poincaré map applied 6 times, this map basically maps that square, we'll call this square D, it maps that square onto itself. But this is the horseshoe map. So the map F, it maps things in D to itself, but they don't all stay there. There's actually a Cantor set of points that stay in this square forever under all future and past iterates of the map. And that's called the invariant set. And that's the set where you can very carefully demonstrate chaos and what it means. And that's related to symbolic dynamics. But this was good. It's fine that we got to this point. So we'll continue with the horseshoe map next time.